Hello, my name is Pascal Lauer and I'm going to present you the paper Polynomial-Time PDDL input size making the delete relaxation feasible for lifted planning. This is a joint work with Álvaro, Torralba, Fišer, Höller, Jörg, Wichlacz and Jörg Hoffmann. As a running example, I will use a modified version of the domain visitAll I called visit1. We have this player and he can move across the grid, and the goal is to visit this one position. If we would want to compute HFF on this concrete task, we would apply all applicable actions until we have reached the goal and then extract our plan like this, giving us an HFF value of 6. Since we apply at least one action per tile, we can choose the amount of tiles as a lower bound for the computation time in this task. Meaning that if we have m indices, we have a computation time of at least m squared. If we want to relate this to the input size, two things play a role: the objects, so the indices themselves, and how they relate to each other, so this next enumeration in our initial state, meaning that our input size is linear with respect to m indices. So we have seen that with m indices we have a representation size of O of m, but take at least m squared computation steps. This doesn't seem really bad, but what happens if we substitute our grid by a 3D cube? If we still choose the last tile we can reach as our goal, the lower bound on our computation time with the amount of tiles still holds up, meaning with m indices we now take m to the power 3 computation steps at least. So what happens if we generalize this to an n-dimensional hypercube? Even if we can't imagine an image for that, we can still choose our goal as the position we reach the latest. Then our representation size will be m times n plus n squared. Without understanding why this concrete polynomial is the right one, you can probably easily believe that there is a lower type polynomial that fixes our representation size. And still our computation time will be at least the amount of tiles if we choose the goal again as the last position we can reach. But then our amount of tiles will be m to the power of n, meaning that we can probably not compute HFF once we scale up the dimension. So what we want to do is put an additional relaxation on top of the delete relaxation HFF comes with. This relaxation will probably lose too much information in some cases, so we want to highlight that and say that we can reintroduce some of this information and in the end show how we can slightly adjust HFF to fit a polynomial runtime constraint when we compute it within this additionally relaxed task. So we have seen that in this visit1 task the problem really is enumerating these tiles, and we want to find some relaxation that allows us to compute heuristic estimates within polynomial time. So why don't we just get rid of the tiles, meaning that we only consider the axis when we relax the task. So now if we mark this tile 1, 1, we will mark 1 on the x and 1 on the y axis. If we mark another tile, for example 2, 1, we will add the 2 mark on the x axis in our relax task. What we just did is to split up this atom at xy into two unary atoms at 1x and at 2y. And it is easy to generalize this idea to an arbitrary atom with predicate p and instantiations I1 to In, and split it into this unary atoms p1 I1 to pn In. Here you can easily see where our name for this relaxation, unary relaxation, comes from, and it is really because we split all atoms into these unary atoms. And then we obtain the unary task by replacing all atoms in the task with these unary ones. So let's see in an example how this would work on the moveX action. Or more particular, we are more interested in just this atom next x dash, which says that when we move from an x coordinate x to some x coordinate x dash, they have to be next to each other. Now if we split this by our unary operator, this means that now this atom has become next 1x and next 2x dash. Intuitively meaning that we only require x to be nearest to some number and also x dash to be near to some number, but they don't relate to each other anymore. meaning that now we would be able to move arbitrarily across the x-axis. Then we would be able to solve any such visit1 task in 2 steps, giving us a perfect heuristic estimate of 2, which doesn't really seem to make sense. So in the paper we describe to reintroduce this information for static atoms, so atoms that don't change across the task, but this wouldn't fit into the time window of the talk. Let's just assume for now that we have some way of reintroducing this information. And then let's try to compute HFF on our unary relax task. If we do this, we mark the 1 on the x and y axis initially, and then step by step we can achieve our new coordinates. Then, as before, we can extract our plan, and suddenly we get the same heuristic value as before. And this looks like we have an amount of atoms and actions which is linear with respect to the indices. But if we inspect these arrows representing our action more closely, we can see that it's actually not one action but multiple actions that we defined here. And my claim now is that we can really just use this one action per arrow and ignore all other actions, and that this will work on any task. And to understand that, we want to take a step back and reconsider why we chose the unary relaxation in this way. And the idea is to lose the connection between all positions in our atoms. And for our actions, this consequently means that we lose the connection between all parameters. What this means is that now for our x2, we have its own precondition, so its own part of the precondition. There are only atoms that just depend off x2 and that don't depend off x2. But there's no connection between x2 and some other parameter anymore. And the same holds for all other parameters in this precondition. So what we could do now is to track which objects are valid for the respective part of each precondition for each parameter. And we could track this in polynomial space. So we need to do this for each action, for each parameter, and possibly each instantiation, giving us an upper bound that is polynomial within our input size. And from here we could reconstruct all applicable actions again, but this would be an exponential amount. So we want to have a look at how we can save the work of applying a lot of these actions, like I showed you before, where we just need this one action to achieve our atom. So let's say we are in this HFF computation where we can only apply this action A or 1 or 3 or 9 or 7. And once we did that, more actions become applicable. The naive way would now be to just apply all applicable actions again. But what we really want to do is to just apply one action per such new table entry. More particular, for each table entry, we choose the action where we substitute the parameter for the new table entry with the new table entry, and for all other parameters we choose the first table entry that became true. So let's rename these objects in the first row as first for convenience. Then we can just list the actions we want to apply on the left hand side. And the thing is that applying these actions will lead to the same state as applying all applicable actions. And the idea behind this is just the same as with our precondition before. Now also these actions have their split up effects, meaning that in our computation we just have to add this combination of action, parameter and instantiation once. And by choosing the actions like I have just shown you, we guarantee that all of these combinations will occur. And since we apply at most one action per table entry, we also know that we only need a polynomial amount of actions we need to apply. So we have seen how we can compute HFF in polynomial time in general on any task, and we have seen that on our visit1 tasks we can obtain the same HFF value as on a non-unary relaxed task. But the second observation will not always be the case. So let's try to extend our visit1 problem to a visit multiple problem. And say our goal is to visit the upper left and the lower right corner. Then you can see a unary relaxed illustration of that on the right hand side. So let's add another goal on the upper right corner. Now our unary relaxed illustration didn't change, meaning that once we have achieved our upper left corner goal and lower right corner goal, we will never be able to tell if we can achieve the upper right corner. So effects like this will definitely harm our heuristic guidance. But we can only find out how much it harms our heuristic guidance in benchmarks, so let's get right into them. For this we implemented the unary relaxation with the corresponding HFF computation on top of it in the power-lifted planner, recently introduced by Korea AI. For our Wizard 1 benchmarks we consider two configurations: close goals and far goals. Close goals meaning that we only have to apply a few steps to get to our goal, and far goals that we have to apply a lot of steps, so almost travel across the whole grid. Our normal unary relaxation will solve any close goal tasks. But once we have a farther distance, we need to introduce the static information we lost, marked by this -d in the configuration. Now if we scale up the goals from Wizard 1 to Wizard Multiple, we can already see that just 3 goals can be very misleading to our heuristic, and that for close goals even goal counting can be more informative than the HFF computation on top of our unary relaxation. But the thing really is that, like I've shown you before, the problem is that sometimes we can't tell if a goal is already achieved or still needs to be achieved. And these far goals show that we can tell what actions we need to apply in order to get to some goal. So why don't we just combine goal counting with our computation? Goal counting doesn't really add an overhead and just does that little thing of distinguishing if all goals are achieved. And if we do this, we can see that the courage score even increases, so we don't just maximize the results we had before. Looking at the overall results, we can see that this combined configuration performs best in most domains. There are 2 domains where this is not the case: pipes world and logistics. Pipes world tends to be misleading for delete relaxations, so this is probably something you would expect to some degree. But historically speaking, logistics was a really strong domain for HFF, so it may be really interesting to reintroduce even more information to our unary relax tasks. But we will have to see how much information we can reintroduce without sacrificing too much runtime. Thank you for your attention.